Good evening, guys. Are you- I hope you're finding these trainings very interesting, the learning experience. And I'm happy to see you all every day that many of you are asking doubts and getting clarified in the serious train. And I also see some of you are really looking for recordings and videos because you might be stuck in exams and don't worry, guys. Reach out to me and let us discuss what we can do. So today is our day 10 of the training in week 3. We are going to discuss about Verilog HDL starting from today. So till now we have experienced a little bit of VHDL and complete flow of development on the FPGA. And in with that FPGA, we have also understood the flow of ASIC designs as well. So we will be understanding in the coming lectures as well. I'll be repeating until you get the understanding of it in the better way. I'll be repeating it. So in this today's training, we will be discussing about Verilog HDL, what are the properties of the hardware description, and major difference between VHDL and Verilog HDL, as you all might have been asking since day one, and introduction to EDA online tools that I have already done, and I have just added this to recap as we are discussing on Verilog HDL and VHDL. We can also introduce some of the hardware description simulation tools in online as well. We have worked in the offline, means we have installed the system into our machine using Xilinx Vivado and the license. That is one way of doing in our own machine. So other way of simulating using RTL or Verilog HDL or VHDL or system Verilog, anything is based on online compiler. There are softwares and web applications available in the online. Through them, we can also simulate. Why didn't I tell this online compiler? Because I want you to have experience in the EDA tool provided by the Xilinx and also understand the FPGA architecture and hardware architecture using the EDA tool, because that is the most required skill as well. And now we are learning how to write Verilog HDL. That is our major key point today. From today till the end of the training, we will be understanding how to make some RTL analysis, like RTL codes, how to construct and build the RTL codes using Verilog HDL. Then going to the Verilog HDL program exam execution, I will be giving you some sample examples as well. See? Then what is HDL? HDL is a hardware description language. We all know by this day. But in the industry, when you want to design a chip, right, you will be getting some specifications based on, okay, my chip should be this, and my should withhold the temperatures of temperature zone from -40 to degrees. That is the ultimate thing that chip extreme sense maximum. Most of the chips will be holding in that. And then what are the other specifications? We are talking about performance. So performance should be very high, like processing speed should be high. How do we achieve speed? By designing the clock free. Like the mode of operations happen inside the chip through logic cells. There shouldn't be any delay. So we should be giving a constraint of delay path, maximum setup path, hold path, all these timing paths we need to decide, and based on that clock frequency and clock is the main key point in the chip entire chip, which decides on the performance. And to design the clock, we have to give the constraints at the RTL stage. Also, we do verify the static timing analysis ports using different EDA tools. In the same way, other specifications are around power optimization. For example, we need to have a lesser power consumption. That is the reason now industry is moving to lower power consumption or nodes, we call it. So low power analysis is another bigger topic in chip design and how the industry is so focusing that area, because whatever chip you design, that should have all these functionality in terms of, yeah, okay, that should be very small, or the internal at the nanometer scale, the transistors and all the allowances should be very appropriately consumed, means in terms of area of the cells that are consumed. You can't randomly design the cells here and there, and you can't use only particular area of the chip, and then you cannot leave the rest of the area as a blank space. You need to consume all the areas of chip efficiently. I'll try to explain in this in the or the tomorrow's lecture. And and as you have already known by this explanation, we are looking for power area optimization. So when you think about a chip, all these factors are majorly considered. You might not know, when you have more heat generated through the chip, right? So then there might be some issue, or there might be a continuous flow of processing, the flow of data processing through the internal connected nets, right? Then the data flow is nothing but the current flow, binary digits that we refer. That current flow, flow of ions, flow of can cause a friction among the wires, and that can clear region of the chip which gets more heat. If you can see the very much processing chip in under the thermoscope, you can understand, okay, this particular region of the. So how do we define all these specifications to the design of by using hardware description language? So hence we are describing, or we are designing the architecture of any chip. So this Verilog HDL or VHDL, any other kind of simulation scripts like system Verilog, are very common in developing and design the chips. So that are common in FPGA development or ASIC development. I'll let you know in the better keep this as it. And then HDL is most responsible for writing tasks. Why it is more essential? We'll get to know by the properties of HDL in the. So this is used to design and develop the implement. What are we designing? We are designing. So let us take a simple circuit of that which involves digital circuit. Digital circuits are gate, or OR gate, and NOR, and all the sequential elements and combinational elements. All these are combinedly connected, and we make some registers out of it. Registers are nothing but can store memory, or that can operate the memory, can process the data, and that can also optimize the flow of data. Anything, any kind of operations to the registers, flip flop, memory elements, many kinds. So what we are designing with H, we write the script, we write the command exactly, that exactly defines the connections of the logic cells. I'll give you an example. So think of it, we are writing some text of lines of codes, and these lines of codes will make the EDA or computer aided tools to design a logic circuit with the connections as told in the, use the logic cells, the gates as told in the text form. We are making this text to define architecture. Okay? So let us move on to the next slide. Now, here you can understand. Let us take an example, very basic example. Don't bother about code, this is behavioral model, any data flow model. Don't worry, we can't judge on the ratio, but we can tell, can be behavioral model or gate level model of it. And then what we are achieving from the HDL output, when we write code, we are writing code for hardware description. Hardware description. There might be some millions of cells nowadays in the chip and lakhs of cells. In the inside the chip, there are cells that make a register. Let us say this dotted box is a edit particular area. For this connection, no, this is not the counter module. I have given some basic example. So whatever you write in the HDL or HDL scripting syntax, that can be understood by the EDA. The under a tool, all the theory HDL code into the logic cell. So remember this, guys. Whenever we talk about language, hardware description language, it is not a software programming or any other web application that we are developing. We are developing the architecture. I mean, what is the functionality of the chip? That is defined. Whether your chip should be a memory element, whether your chip should have a processing a kind of application like software processor we have developed, or whether your chip should only work as a counter. Okay, that depends. That is based on the HDL that we write. Now I'm telling a counter, might be this chip here, this is the, that chip should work only the counting part. So when I write HDL, all the logic cells are connected, done, and the data flows in this left to right direction from the input to output, and processing happens. And then if it is connected to one of the LED, then what is the output on the LED? This is the FPGA, suppose FPGA chip, not the board. Okay, now FPGA chip, we have given HDL language, HDL language to the EDA, and EDA has made the processing and also decided the inputs and outputs. I'm just giving a flow example, and now from that output connected to the LED pin, and in the LED pin, what is the application we are looking for? Counter. So what type of counter? Here I have used 4-bit. So output should have 4 bits. So on the 4-bit counter, what is the maximum thing that we can achieve? You can say 0. So all this we have achieved. Hence, so what we are looking at, all the counters from 0 to 9, and what it does is it repeats again. And it can go beyond as well based on the LEDs that you can go. So I will show it in the online EDA compiler as well. So we have different types of EDAs, different types of vendors. We is Cadence, Siemens EDA, Spray, and there are many. I will show it to you. So understand, we are writing HDL to make this kind of circuits. This is the digital circuit. I have made it a random, but this is so. So now steps of HDL script development. As I have told, from text format, specific syntax, then using EDA tools, they are giving something to the EDA tool. Where we are developing HDL code on the EDA in the but when we click on run, right, EDA tool will extract this entire information and it will check for the functionalities. And now these specifications, HDL written, we should get the specifications based on the clients, based on the customer requirements. For example, if we are developing FPGA for a robotic arm, yes, so for that robotic arm application, we need to develop the HDL, and then using CAD. CAD is nothing. Here the algorithms embedded in application. The advanced tools that is now called as electronic design automation. So converting the design into the connected logic circuit, internal cells for the specific or application or for different. So now this EDA tool uses or utilizes the HDL and understands, okay, these are the logic gates that we have to use, and between these logic, these are the connect we have to. That is what is made, developed by the EDA. So these type of connections by wires. So these will be wires. These will be in, might be out. So better understand. And now going to this next step, use the HDL converted netlist file. I mean netlist. How do we get the netlist file? Okay, when you say OR gate in the text format, actually in the physical presence, we require a logic gate. That logic gate nature can gate be something. I mean, this OR gate requires a voltage of 2 point and also temperature. Sometimes they M40. So that kind of nomenclature will be available in the libraries. Libraries are nothing but they are the actual developed algorithms or pre-developed codes for all the elements that we use in the description of the hardware. So these are already available in the library. As you imagine a college library or university, we take some book that is already available in the library shelf. As the same way, we are taking this OR gate technology with 22 worlds technology. That OR gate technology will be abstracted from that existing libraries. There might be many OR gates with 3.3 volts, and some use 5 volts if they are operating much more number of data bus. So depending on the OR gate that you are required and as per the HDL that you specify, you will be getting OR gate from the libraries, and that library cell is attached to your hardware description. Until unless whatever text format you write, that won't be understood on the FPGA board. What hardware FPGA board is looking for? It is looking for, okay, I have these logic gate OR gate cells of 2.2 volts. I have logic OR gate cells of 3.3 volts. Which one I should use? You have written OR gate application, but whether I should use this OR gate with 2.2 volts or with this OR gate with 3.3 volts, it will never know. It has all types of OR logic gates, and it has all types of AND gates. It has all types of memory elements. Which type of memory element do you want it to be used on the FPGA? So for that thing, you need to take the HDL code and synthesize it. Synthesize it nothing but applying a layer on the HDL code by adding logic gates or the library elements according to the technology that you are looking for. Whether you are looking for 7 nanometer OR gate, 4 nanometer OR gate, or 1 nanometer OR gate, or what are the logic cells that you want to decide. You want to decide on 14 nanometer. So these type of technology constraints according to the physical device. At the end of the day, your chip or your FPGA architecture or FPGA hardware board, you should think in the perspective of hardware. When you are developing some architecture in respect to hardware, you are developing the text code. That won't make sense until you understand the hardware architecture. So that is the reason I am telling netlist. Netlist file is generated from the synthesis. Synthesis is nothing but a process of converting the hardware description language into the gate level netlist. Gate level netlist is nothing but what are the all the logic cells. You won't be doing only for all or logic gate. It will be doing for all the logic cells that you have written in the HDL code, in the complex HDL code, where you are using the processor counter, clock wizard, and system debug, and also where you are using address protocols. If you have been using all these types of 8 to 10 modules or blocks, for those blocks you need to write Verilog HDL or it can be generated, and for that generated Verilog HDL you need to synthesize a netlist. So this is the major step. Until you declare or define the netlist, netlist means the technology or the type of cells that you need to be using on the hardware, your HDL language is of no use. So keep in this mind, guys, whatever HDL language you write, it should be synthesized to the netlist level. Netlist is nothing but what wires should be connected. There are different types of wires with different widths inside it. So whether you are using 4-bit bus or 8-bit bus or 16-bit bus or 32-bit bus, there are different sizes of the address bus or data bus. So you need to mention, right? So that kind of declaration and definition is done in synthesis. Synthesized netlist file is the key role. So now you all understood what is synthesis. So keep in mind, guys, HDL language will be converted to the netlist that can be understood for hardware design and implementation. Implementation is okay. Now in synthesis, you have declared, okay, I have written OR gate, very basic last time. We have designed OR gate. We have mentioned only OR gate or A or B. We have mentioned one. But here in the synthesis, we are synthesizing it using EDA. After synthesizing netlist, we are just declaring, okay, for this OR application or functionality, use this OR gate. Okay, good, very good. But what type of wires to be connected between this OR gate and to the next neighboring element? It might be AND, flip-flop or mux, anything. So that kind of clarity will be done, will be connected in the place and route. Okay, this OR gate is very much near to the input of A. So input ports and this OR gate should be very near. Place this OR gate near to this. How do we place? No, it is not physically placed. We have OR gates in different areas. So we take OR gate from this sample, I mean from this nearby port, and we enable that OR gate. So that is what placing in different blocks. I'll show it in the example of the design. And yeah, that is the structure of, I mean, steps of developing a HDL script based on the hardware that now moving on to the EDA tools, as we have all known how these EDA tools have evolved and also how this FPGA have been. I've been introducing you to the history of FPGA development, so the EDA tools. Now, some good companies you should be knowing about EDA tools. Intel Altera company is not Alter, it is Altera. And then now Intel Altera company provides Quartus Prime and AMD Xilinx gives you Vivado ISC. I have introduced you to the, and there is one compiler for DC by the synopsis, as we do synthesize the actual chip design in ASIC design flow. Now I am in ASIC design flow, and in the FPGA design flow, we have two strong leading EDA tools that are, and Mentor graphics. It is common in every platform, whether it might be ASIC or whether. Remember, guys, Intel and AMD mostly focus on FPGAs, and AMD Synopsys and Siemens, all these also focus on ASIC development. EDEC Rivera Pro is an online compiler. Also, you have compilers available offline as well. Offline is nothing but which you can download onto your. So yeah, why EDS are used? EDS are used for developing very large scale integration designs, and mostly around 10 lakh transistors. How do we design one on one? How do we design all the transistors manually? No, not human possible task, but humans made it possible with EDA tools. So that's a major advantage. Now, other EDA tools. What are the EDA tools types? EDA tool types are nothing but have different steps in the development of chip design. In the different developments of chip design, one is synthesis, one is design, implement, verification. Major steps. So whenever you remember about the flow, you can get okay. So whenever you think about designing a chip in the development flow, you come across RTL that we have explained in the yesterday's class, flow of FPGA. We come from the HDL language, then we synthesize. After synthesizing, we need to verify in the simulations. Okay, we simulate. Simulation is nothing but testing virtually on the computer machine itself, not on the. Then design, implementation, verification. So some tools are in synthesis. For example, in synthesis EDA, we have design compile. And for design implementation, we have ICC2 or Fusion compiler. These two are provided by Synopsys itself. So, for example, synthesis, simulation, design, implement, verification, all are done in one tool, Vivado, Xilinx AMD. So, Vivado tool does all this part in one. For the FPGA development, for ASIC chip designs, so synthesis tools are different because the functionality or the mode of operation in that process, in that step, is different from the next step. See, if I design at the IC level, at the micro level, for the physical nets to be connected and physical cells to be placed here and there. That is entirely different from assigning the libraries to the hardware description language. So these particular tools will only do some particular functionality, and these particular tools will only do design part, synthesis part, and RTL writing and verification. Some do only timing analysis. So for timing analysis, we have another tools. So those come. So what my intention here is, don't confine to only one tool. That is the reason ASIC chip design industry is very complex. They work on 3 to 4 years or 5 years on developing a single chip which will be more efficiently working in many types of applications in the commercial purpose. So they will launch after 3-4 years, but they work before 3-4 years. So it is like different tools should combine together, like different departments. Some will be synthesis engineers, some will be design engineers, some will be DFT or design verification engineers in ASIC chip design. Not in the FPGA, there will be like application based, R&D based, or product development based and testing based. So it depends. So depending on the departments, we have defined the tools. But here is the catch, where in the upcoming world, in the world of artificial intelligence, what these tools are doing right now is people are combining all these tools into a single part, and then they're executing the flow in a single click. For example, everything is automated, and in that automation, we have separate steps like separate tools. Now they are combining all the tools into a bigger tool. Simple. And then again, they come up with other advanced tools separately. Later, they will combine all those tools again. So it is a process of evolving. That is how we have evolved from computer aided tools to the EDA. You might have remembered we have told about OEMs, original equipment manufacturing tools that were provided by the manufacturers. So with those tools, we used to design the ICs. But now we have combined all the functionalities in the IC design. We have made a computer aided tool and then EDA tool. Now EDAs are automated again. We are combining EDA tools, different set of EDA tools in a flow. I'll explain it in the design flow, the upcoming lecture, and then we are utilizing it. So this is it. Just to make you understand, we are not having only one tool. We are not having only Vivado tool. We have different tools by different vendor. So what are these tools do? They do different set of tasks in the development flow. Synthesis, implementation, and some do verification, some do timing analysis, and some do bit generation. Something. So that is the advantage of EDA tools. It has made our task very easy, guys. And you want to design a memory block using lakhs of transistor cells, will you design? You have to use EDA tool, write HDL for it, write HDL language for memory block, write it, and then boom, your memory block will be developed using EDA. So EDA tool does the major part of. So one best example for digital circuit, how these digital circuits are in. I have made random equation. Let us take a Boolean equation of, what is this? Product of sums? No, product of sums. So yes, times with vector. So okay. Now this, from this POS, what I want to design is how to design these levels of cells that to be. Implementation is nothing but having connections done and also having the functionality applied and ready for verification. Implementation. Synthesis. Okay, I am asking for OR gate with 2.2 volts. So this name or this library cell is assigned for the OR gate functional code. So this entire thing can be an example of lookup table. How it is an example of lookup table? Because lookup table will be shown for you, but inside those SRAM static RAMs, and in that blocks, this entire functionality will happen. This is a functionality of some this operation. If you want this kind of particular desired for you guys, today I am giving a task. Give some values, random values, 1 0 0, and see what is the output you are getting. Let me know, and you can not in the comments, you can give me in the WhatsApp screenshot as well, whatever you have worked. So this is how the lookup table works. Lookup tables are stored in the SRAMs, and in the SRAMs, the operations happen in the based on this OR and AND gates or XOR gates. Or you can implement any cell, any logic cell. So based on the requirement. So check the functionality. So this is how you design a circuit. Entire this circuit can be designed in the Verilog HDL. Okay. Next, properties of HDL. As we all know, we are developing a hardware description language. It should have some properties. I mean, what are the limitations and restrictions, or what does this HDL language consist of? Operations. It should operate on certain terms and conditions, standards made by IEEE or somehow. So that standards will help the global engineers to work on this type of language wherever they want to apply. So the program is executed in parallel. Remember, guys, this parallel. What is meant by parallel? I'll explain. So it runs continuously. Good. We are looking. It should work continuously whenever we switch on the FPGA board and whenever we turn it off and switch it on again for the application. So it should run continuously. If you switch off, it shouldn't go reset again. So it shouldn't go reset again. And then what we are looking at is HDL is time specific. Yes, we need to mention the clock or the time that needs to be operated with the data flow. And then the flow is, we are writing lines of code. It is text format. Then it will be gone to some cache variable by the EDA. In the EDA, after EDA develops, it will be processed in a cache memory or in the cache variable. And then we get the output waveform. See, this is input and process and output. Every time I talk about any application or any flow of development, we are talking about what is the input, process, and output. Simple. And coming to the parallel execution, right? See, in some of the programming languages other than this HDL, let us take C programming, it has a syntax where the tasks are applicable. I mean, in the C program, the lines of code are operated in a sequential way. But in HDL, if we do in a sequential way, no, it takes a lot of time to go through each of the logic cells and work this data from input to output. So for example, if you have 1 0, if it is going in a sequence to the output and to the logic cells. So for example, if it is a sequence, right? it should go to each of the cells and it should process the data, and then it should, in a rough example, very dry, should go, it shouldn't go like this. That is why you are developing HDL. And if we are writing only one OR gate, right, from the data, one to one, it goes in this way through the levels, or it can go in this way. Whatever the elements that are to be used, for example, you have a data 10 starts from this logic gate, and it should use the second one, and it can use the third level AND gate and fourth output. Done. But if it in a C programming, it first checks all the levels of OR gates. Okay, then it checks, okay, I should use, and then it will check again these logic gates, and it should use this there here. In the C programming, it checks all the logic cells. Will check all. If it is okay, will go through the first one, and in the second, the third level, if it is using this OR gate in AND gate, it will come here and the data goes to the, it is taking more time. So C programming, the functions or the set of commands or lines of operation work in a sequence order. So one after the other. That takes more time. But if you can execute all the commands of hardware description language in parallel, right? Whether you are declaring input and also processing the input immediately with the begin function. So uh, there happens a immediate response at the output. So that is what we are looking for. So hence, when you write a Verilog HDL code and when you compare it with the C programming, which one executes first? Verilog HDL. Hence, we have a winner. So that is the main response. Parallel. Always, we write always at the rate POSH or always at the rate input. Right? That is nothing but it runs continuous. Other property, and time specific, very sensitive with respect to the timing, because entire digital circuits will work with reference to the clock, one clock, and all these elements should be in sequential and synchronous uh, to this clock. So synchronized clock is the key element in digital circuit functionality. So moving to the next thing, example code. Now let us take a random design and let us execute this. And now what are we looking at? Looking at a plus b into c plus a. So that is our output. So we have made this in a simpler terms, and now this data a plus b will be stored on the wire D. Hence, after logics, after logic gates in the internal levels, right, you can name these interconnects as the wires. I'll repeat everything in the actual structure explanation. Now let us understand what we are achieving from HDL language. We are achieving logic connection cells in the physical environment. On the FPGA hardware you require. So we are achieving hardware by based on the Verilog HDL text code. So module random design underscore design. This you can name it as you like, but it has a syntax sensitivity. You need to write all the lowercase letters and underscore in it, and you need to declare input out. See, forget about whether this is a behavioral model or gate level model or data flow model. We'll come across these things. Any one of these sets you can develop, but ultimately you are getting logic cells, hardware, and interconnects, hardware, and input output again, and the processing happening. Same, that is what we are achieving. So module you have named, you have named all the wires, output ports, input port, and you have to declare input ports, wires, and always at the rate inputs. You need to mention A, B, C, D, E, E, all the inputs. You need to start running on these things. When you set it as always at the rate inputs at the input data flow, if the input data changes, So if there is only a data change, if this is 1, it will work, and if it is 0, it will work again, and if it is 1 again, it will work. Until unless if there is a 1 and if it is 1, it won't change any little bit. So all the data input ports or variables should be changing. So for that changing, for that continuous functionality, if it changes, it should work. And if how we are declaring, always at the rate changes of the inputs. So changes the inputs, you need to start processing the entire thing. So if d this is an assign operation, guys. Whatever functionality happens here, processing between input, that needs to be assigned to the wire D. Why do we call wires as D? Because we are assigning a variable here for the output of A and B. So that is how the process happens between input and output. So now, as we all know, functionality AND gate, or function, and end module. End module is related every time to the module, and this end is the stopping of the process with the begin. So every begin comes with an end, every module comes with an end module. So this is the basic syntax. You understand simple way, and then go to the counter Verilog HDL. So then part 1, part 2, part 3. Why do I write part 4 and part 5? Very simple, guys. To understand Verilog HDL in a better way, let us divide this entire syntax into parts. What is the first part you need to write? You need to mention time scale units. Don't worry about why do we write this tick and time scale and 1 nanosecond. And these are the syntax and keywords. I'll explain it. Now I'm introducing you to the Verilog HDL in this way. That this is how you should think. Okay, now we have to write Verilog HDL. What are the major steps that you need to take? So first we need to declare time scale, and time scale is nothing but whether our Verilog HDL is time sensitive. We need to mention the units according, and then part 2. So in the part 2, we always declare the module first. What type of module that you are working on. So to define module name, is module name, and we need to define what are all the output ports and input ports that are available for the module in the design. So counter, when I say counter, you can ask for how many bit counter, or what is the what are the pins available in the counter. For every counter, it is a basic example that clock, reset, and basic ports. So input clock and reset, output 3.0q. It's nothing but when you declare output, right, you need to mention the bit size. So this is the size of the output, right, which has 4-bit capacity for the output. It can't show you beyond the 4-bit. So wire, clock, and reset. So why do we call wire, clock, and reset? Because these are the inputs. Always inputs are wires. Register here, it is a variable or some component. It is not the register with logic cells and flops. So just register is nothing but a element that we are designing. So here register is can be a port. So that's what register is, an output port. So all inputs wires, all outputs register. So and in the always continuity functionality, now we have declared name as well, right? I'll show you in the example using EDA tool as well. So always at the rate pause edge clock. So we have declared at the pause edge, like is the clock. So at this point, the actual hardware will be enabled. So so at this pause edge, the clock enables the functionality of the hardware. So after that, we will be going to the beginning of the process. So step 4, part 4 is nothing but step 4, process begins. Whatever functionality of the counter, right? Counter is, it should start from 0 and it should increment. Increment is the basic operation. So it should increment from 0 to 1, 2 to 3. So it should go beyond in this. So hence, this is what it should look like. And then part 5, AND module. This AND module will be started. After you write some if loop, the functionality of the counter, you need to end the process, and then FPGA understands, okay, after certain thing it ends, and end module. So end module is like, okay, we have designed the module, okay, take this design. That's what we are declaring. So every Verilog HDL will basically have these 5 steps. One is time declaration and module definition with input and outputs declare. Every Verilog HDL program you see the module declaration, and this is to be there before beginning the process. So when do we begin the process? Only the pausage clock happens. So we can also mention negate clock. That is example. Now take this counter example, guys. Here you can pause. You can take some good photo of this air code. I have mentioned this commenting as well in the Verilog HDL. I'll explain it again in the next class. So today it will be overwhelming to you all, but understand this will be the structure. So what is the part 4 called? Everything I have declared, take a screenshot of it. Why? Because we will be implementing this counter and also the test bench Verilog HDL code for the counter on the EDA online platform. So in the tomorrow class, so this is the Verilog HDL example for counter. This is what I have written here. And coming to the test bench Verilog HDL, how do we write test bench? I'm just giving an introduction. I'll explain how to write test bench from the basic syntax itself. I'll explain in the later coming classes. But today we are introducing ourselves again to the Verilog HDL and test bench Verilog HDL for the counter module. So in the part 1, okay. In the test bench as well, we have to declare timescale. Declared, done. In the part 2, declaring the module for test bench. What module we are designing? We are making a bigger circuit for the primary circuit. Primary circuit is counter. What is the test bench circuit we are creating? Counter underscore TB. So this counter underscore TB will check the functionality of the counter that we are looking for. So again, guys, remember, some of you are asking, this test bench VHDL, we ignore this on the FPGA architecture. We don't want this test bench. We are writing this test bench to check the hardware description language code in the text format, whether it is working using simulation. So that simulation we have done using timestamps. So we can check it. So counter underscore TB. So here is online EDA. No need to mention IO, because now I will show you the EDA compiler, online EDA compiler. There is no requirement of declaring the IO ports as we have declared here in the counter module. So this is counter test bench. So in the test bench, we no need to declare IO ports again, as it is already instantiated to the primary source. When you look into this, code, you can see this is the online EDA compiler. So where you can also see EDA playground, and you can register on your own, and then go to the languages. You select system Verilog, and after you select system Verilog, come to the tools. So we need some online EDA tool vendor. We have Aldec Rivera Pro. This is the EDA tool, and you can see synthesis. We have Aldec synthesizer. This was given by synthesis. All these things, and you can also the name output file name, and click on this open EP waveform, because after you generate output, right, you can see it in the radix format, in the timescale format, the timing simulation. So show output file after run, that enabled. So some simulators, we have compilers based on C++, SH, Perl and Python, and any other Verilog files that you want to select. And some of these are the open vendors where you can write the Verilog HDL code on this side. SV, don't worry guys, system Verilog or Verilog are similar, but system Verilog uses OOPS concept for the advanced level testing in the chip design industry, in ASIC design. So the system Verilog is again the developed version, most advanced developed version of the Verilog. So now in the test bench, let us understand. I can't zoom in as well. So part 2, go by step, guys. First step, we have declared the time scale for units. This is how you can declare, and this symbol is nothing but tick. It is above the tab button, like simple tick mark. So that tick mark and time scale, that is how it understands the, okay, this is the time scale that we are writing this. So these are the macros which are used in the Verilog HDL at the time of execution. So now what we are declaring is timescale 1 nanosecond. So entire code or entire functionality of this Verilog HDL, the timescale units are 1 nanosecond. When we have written hash 10, it declares 10 nanoseconds. Hash 1, 1 nanosecond. Hash 500, 500 nanoseconds. So that is how we declare. Let us come step by step. Now module counter, register clock reset, and wire 4-bit Q output. So we need to declare input registers and output registers and input wires. So but in the test bench, right, see, compare with the Verilog HDL. Here input we have declared clock and reset, but inputs are always wires, the Verilog in the primary source. But in test bench, we have to uh, feedback connect in the reverse direction, so that whatever input you get, it should be connected to the output wire, and whatever the output is connected, this should be taken as the input reference. So if we check in that way, then we can check the process. Okay, this entire process is hence the reason registers are now declared as clock and reset, and wire is but out. So hence the connections are made in this way. Now give some label counter unit under testing. Now this is to be understood by the FPGA, right? We need to declare a label. Remember, this step is also crucial. So clock, reset, and Q, these are the input and output ports. And you are mentioning counter. What is this counter? You have used. Okay. Within. Let's go to the step 3, where the actual testing process begins by the initial begin. Remember guys, whatever I say here, you need to remember these. I mean, if you understood, okay, after this declaration of the module, we are beginning the process. After beginning the process, we need to show the output. So output can be shown in this way, and then we need to end the module. So I'll repeat again, declaring the timescales. We are giving the input, we are giving the process, and we are showing the output. // output, and now process begin. So when I tell you, right, when I tell you process, and then here is the input. Got it? This is how you write Verilog HDL or test bench Verilog HDL. Both are same. Same means you write input process. Now in the process, every process begins. What is the process in test bench Verilog HDL? We're testing, verifying. Verifying is the process. So that verification is nothing but done in this way. So if you can go, we need to set the clock as 0. Okay, should be 0. And reset should be 0. Initially they should be at 0. That's what we are declaring. Initial begin. Initialize. So begin. And then after 10 nanoseconds, now we are declaring the clock. So after 10 nanoseconds, hash 10 is nothing but 10 nanoseconds. After 10 nanoseconds, you need to make it happen if reset is equal to 1. Okay, now reset pulse is 1. I'll show it in the declaration. Here, come to this part. Those are same, guys. So now the process begins in the step 3, initial begin process. Initial begin is nothing but process begin. So that's why I have written it. Top, you can always, now clock is 0. Is 0. Reset is 0. So 0. And now after 10 nanoseconds, okay. Clock. Clock is 1. So reset is 1. Until then, reset is 0. So reset is 0. The reset is 1 now. And after 10 nanoseconds, it is, what is after 10 nanoseconds? 20 nanoseconds. The output is 0. So reset is 0. Done. Now reset is 1. Reset is 0. So from 0 to 10 is 0. 10 to 20. So here it is 0 seconds. It is at 10 nanoseconds. And it is at 20 nanoseconds. Understood? So after 1 nanosecond, after processing all these things, so why do we make reset 1 and 0? Good question. Because in the Verilog HDL, the counter Verilog HDL, if pausage, if reset. If reset set is enabled, if reset is functionality, if reset is 1, if reset is, okay, now reset is operating. When do we get reset enable? We got reset enable this 10th nanosecond. From the 10th nanosecond. So Q is equal to output is, and now reset is 0. Now reset is 0, else counting. Counting, right? Counting from 0 to 1. Again, the loop comes to the next part again. In the next clock cycle, it will be 1. Now the Q is 1, right? Q is assigned as 1. And this goes to 2. And this will go in the other loop. And 2 comes here. And then 3. And 3 goes here. And 3. Now it comes with 3 plus 1 is 4. So this is how the counting happens. 0, 1, 2, 3, 4. So that is how the counting happens. Okay. Now coming to the process. This is how the process happens. Now we need to display it at the output part. Now we are displaying. How we are displaying? We are using after 1 nanosecond. Declare $monitor. Monitor is to showcase the display continuously for every single second. When I execute, you will be seeing $time Q is equal to %d output. You store it in the element Q. This is the syntax. Don't worry about syntax. This is how it is written. I'll explain the syntax from the keywords as well, how to write all these things. But $time okay, it will showcase at what time it has been executed, and also to represent, right, percentage d, it is same as the declaration in the C program as well. So q is equal to percentage d. So whatever the output is there now in the q, that is displayed as the ampersand, guys. Not syntax. Understand, okay, to display any variable, right, we need to display the integer variable. So in this way, for the, and that will be displayed from the queue, from the output. So this is to enable the output display. So next, after 500 nanoseconds, stop the process. Stop the reset or stop the if loop or whatever it has, if block and else block. Stop that process and come to the process should end. If if it begins, should end. If the loop begins, you should stop. You can declare it stop. Until unless you declare stop, it won't. So then coming to the step 4, output. Now you have mentioned output to monitor, output to display on the display. So you need to go to the step 4, and then you need to declare this way. After 10 nanoseconds, clock shouldn't be following the clock. It should be negation clock. So it should stop after 10 nanoseconds. Hash 10 is nothing but after certain amount of time. What amount of time? 10 nanoseconds. Initial begin, you can begin the process, and dump file, dump wheres. So this is again a declaration you should remember. If you write few more lines of codes in continuous way, right, you will be getting all these how to write and all. So that is how you enable the display. And this is for online EDA tool. For example, you are using this EDA platform, right? I have to mention this to enable. Okay, this EDA platform understands a platform understands. Okay, they are asking for dump.vc and to show a waveform to this. And this is again another process, showcasing another process of displaying. And first process is going through the testing of the functionality. Remember, testing of the functionality. And now the second process is displaying the output. So this is how you set up tasks differently. So now after I have, you need to save it and then run. You run this, show you the output, show you the waveform. But before that, you can see, okay, at 21 nanoseconds, 0, 30 nanoseconds, 50 nanoseconds, 70 nanoseconds is 3, 90 nanoseconds it is 4, 110 nanoseconds it is 5. So process, it is taking 20 nanoseconds time. If you can change the time from 10 to 5, it will take other loops as well. So what is the count occurring in the terms of 9, 10, 11, 12, 15, and the count begins again, process begins again. And after 500 nanoseconds, we said stop. If I say 1000, if I save, run it again, I can see another loop of 15 numbers. See, at 1000 waveform, very good way. Show it to you. So 1000 nanoseconds, it will stop. That is how we can see the counting app appears. And now this is connected to the LED board. Just imagine if it is connected to the LED board. Now you can see the display. Okay. These LEDs will be blinking. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. It shows till 15. Yeah. So it is possible. That is how you write the Verilog test bench Verilog HDL with reference to the Verilog HDL you have written. So depending on the Verilog HDL, you can vary the test bench Verilog. Test bench Verilog HDL is a file. used for only verification side. So that is how. And basic Verilog HDL history. In 83, it is been standardized by, and latest versions that we are following in the terms of libraries, and across the globe wide rangely used is Verilog HDL. That's how I understand. Than VHDL. VHDL is a old language used by most of the European countries. And VHDL, the definition is very high speed integrated circuit hardware description. Very high integrated. So that has ADA algorithm, very old algorithm that. And now Verilog HCL consists of C language and in the C language we also, as we normally do. So that's how it has been developed from the concepts of C programming, very old program. Compared to VHDL, testing is easy in. That's how I also prefer Verilog. It is better understandable in the Verilog HCL. So now I want to explain the waveform. So you can change the radix, okay, decimal, it and binary. You can see as and reset is one. It started, has stopped at the last point when the clock reached 1000 nanoseconds. These are in the terms of picoseconds. And when you zoom in, right, you can see first is start from 0. So after 10 nanoseconds. Okay, after 10 nanoseconds, it starts. 20 nanoseconds tends to 0. Again, at the other passage clock, the changes. So 10, and now after 10 nanoseconds, it has to change for 1. In the same way, it is changing from this 0 1, and 1 0 is nothing but you can. So that is how the waveform looks like. To write that EDA, to write that display, you need to mention this part after one time time scale display. Then it's a parallel process, and after 1000, and for displaying this EP waveform, go to this left side menu bar in tools and simulators, open the EP waveform and click on this. Mention a counter name. I have mentioned it as count, and then you can save it. And after you save it as it is, you run it, you can see the as I have shown you. So this is how the functionality works. Any questions? Please ask us in web groups. Thank you for all of your participation. Please do watch everyday videos as they have time restriction. Complete as possible. If you need recordings, please contact us. LMS Access. Thank you, guys. Thank you, Manan.